Hello, my name is Ramla Qureshi and I'm a PhD candidate at the University at Buffalo researching performance-based design approaches for structural fire engineering. On the 14th of June in 2017, a fire broke out in the Grenfell Tower in London, causing over 79 deaths and substantial property damage worth millions of dollars. Regrettably, this is not an isolated incident. In the United States alone, structural fire losses cost over 1.9% of the total US GDP in 2014. The basic objective of fire safety engineering is to protect human life and to prevent the loss of property. While we can burn up full-scale building models for understanding global performance under high temperatures, these tests are extremely costly and are therefore seldom performed. Also, large-scale tests can be difficult, not to mention dangerous, and require specialized instrumentation to glean useful data from a burning building while it's on fire. Currently performed standard fire tests for calibrating fire resistance of structural elements only consider a singular column or beam, with either a fixed degree of freedom or a constant force as a boundary condition. Often, these element-level tests neglect interaction with adjacent framing members. Meanwhile, robust numerical models are limited in their ability to capture post-failure performance of the structure. A smart alternative to this issue is to introduce a hardware-in-the-loop testing technique, where instead of a static support, servo-hydraulic actuators update the interfacing forces and displacements between a test specimen and a virtually modeled surrounding building frame in real time. This works quite well for application in structural fire testing up until the constantly degrading material stiffness of the heated physical specimen starts to introduce instabilities within the control algorithm, and the conventionally used hybrid simulation framework falls apart. My research focuses on completely decoupling the control algorithm from the physical test specimen. Instead, I tune the actuator such that the tip of the actuator behaves exactly as the rest of the frame would have in reality, in response to the displacements and forces developed within the physical specimen due to temperature effects. I am investigating the response of a column situated in a steel frame, which buckles at high temperatures and could lead to a global failure. My control algorithm for this setup uses a control input that tunes the actuator dynamics in order to have an output boundary displacement that matches the corresponding displacement from the virtual frame regardless of the changing properties of the test specimen. This research will contribute to column failures as seen in progressive collapse scenarios, not just due to fire, but any other extreme event. Thank you.